From the previous lecture, we learned that the most important aspect of machine learning are input data, expected outcome or labels, and evaluation metric. Before we can train our model with the above three elements, we have to first structure our data. Effective data structuring is important as it ensures that the input data is in a form that maximizes the efficiency and accuracy of the machine learning models. For instance, in vision tasks, structuring may involve formatting and normalizing image data and annotating images with precise labels. In the previous lecture, we discussed objects like classification, segmentation, and detection. Remember, these are not the only objectives in AI, but are specific to vision deep learning. Since this course is on vision deep learning, we will limit the scope of the dataset, so the input for our model will be an image. The type of videos that will be the input depends on the specific vision task we are working on. It could be medical images for disease detection or road videos for autonomous vehicles. We'll change these inputs into a matrix with values for each pixel. For each pixel, there will be a value associated with it depending on what is in that specific pixel. In the case of an image, which is two-dimensional, we have an n by n matrix. In the case of medical image processing, CT scans yield three-dimensional matrix by introducing a quote-unquote z-axis. Since in the case of a video, we have a stream of images, we represent it by a three-dimensional matrix as well, with each two-dimensional matrix representing an image at a point in time. We can have a two-dimensional matrix having values samples, which represents the number of images, and height of the image, width of the image, and channel, which could be RGB, in which each pixel will have a red, green, and blue values comprising the pixel. So, this is a way in which we can transform an input, in this case an image, into a mathematical representation. This notion of a channel is particularly important because it allows for different types of image data representations, which we will explore using the example below. For a grayscale image, if we denote black as 1 and white as 0, we can represent shades of gray with values between 0 and 1 if needed. In this black and white image, the image can be represented by the following matrix. Since our example isn't a video but an image, we would have 1 in the samples column of our matrix, whereas a video may have a value greater than 1. The height and width are both 3. And 1 channel because it's a grayscale image. In the case that there's only 1 channel, we don't have to specify the number of channels, but in our practicals, make sure to include 1 if there's only 1 channel. And in the case of a color image, we utilize the RGB color model. As commonly understood, we can depict any color through combinations of the 3 primary colors, red, green, and blue. So, for the color image example we have here, just as before, since there's only 1 image, we place 1 in the samples column, and the height and width are also 3, same as before. For the number of channels, we have 3. For the red pixel, the value will be 100. In the case of a green box, the value will be 010. In the case of white boxes within the grid, while white light is traditionally produced by the combination of all lights, we've chosen to represent it as 000 for educational simplicity. Think of it as an absence of paint in our representation. Conversely, when you mix all colors in a paint scenario, you would achieve black. Thus, we represent a black pixel as 111, contrary to how light mixes. The blue pixel will be 001, and then the yellow pixel, since it's a combination of red and green, would be 110. Although we've chosen to use the combination 110 in this instance, in an image, the pixel values are represented so that the sum of the attributes equals 1. So, in the case of a yellow box, it would be 0.5, 0.5, and 0. In instances where we have 3 channels, Each pixel is represented by 3 entries, each denoting the proportion of each basic color, red, green, and blue within that pixel. You might wonder whether we just use one channel for black and white images and 3 channels for color images. It can vary depending on how the data is structured in the matrix. For example, in the field of astrophysics, imaging isn't limited to visible light. To explore different properties of celestial objects, we sometimes capture images using infrared or ultraviolet light. Similarly, in environmental monitoring, multispectral imaging is used to capture data at specific frequencies across the electromagnetic spectrum. These images often include channels for different types of light beyond the visible, such as near-infrared, to analyze vegetation, water bodies, and other environmental features effectively. In such scenarios, the matrix might have multiple channels for different types of light. The first channel for visible light, the second for infrared, the third for ultraviolet, and perhaps a fourth for radio light, culminating in a 4-channel image. And don't forget that this is just one example of how channels can be utilized. To provide another example, in medical imaging, such as with MRI scans, videos might be categorized into different types like T1 and T2, each highlighting different aspects of the tissue. Here, we might use 2 separate channels to represent these distinct types of MRI scans, allowing for a richer, more detailed analysis of the medical images. In the case of PET-CT, also another example in medical video processing, we might have a video with a new channel called contrast medium, having 2 channels in this case. This example is an image from a CT video. In a CT video, the brightness of light goes from -2000 to some positive values. These ranges represent the density values, measured in some units, which help in differentiating various types of tissues based on their density. Since our objective is to see specific parts within the area that take a scan of, we might include a channel for 0 to 1000, and another channel may include negative numbers up to 50. Window settings are important for improving the visibility of specific features within an image by adjusting the range of pixel intensity values that are displayed. These settings involve setting specific window levels and window widths, which can be tailored to enhance different aspects of an image. This technique is widely used across various fields, not just in medical imaging, to highlight details that are vital for accurate analysis and interpretation. The reason I included the example of an image from a CT video is to show an example of how we represent an image in a matrix. There's a library, SimpleITK, that has a function that allows us to transform an image into a matrix of pixels. The shape of an image represents the dimension of the image. So in this case, height is 512 and width is also 512. It may be a little hard to see in this video, but the X and Y axes go up to 512, corresponding to the dimension of the image, which is 512 by 512 pixels. We have talked about how a CT scan requires a 3-dimensional matrix, but since we only have a single picture, we don't have the Z-axis and only the X and Y axes. So, with the help of the function from the library, we can transform a raw image or video file into a matrix, which is a mathematical object. Now, how do we structure the labels? In medical image processing, for example, in classification tasks, we can represent conditions like benign or malignant with binary indicators or 0 or 1. Note that we do not use the text labels, but rather resort to numerical labels. There is a problem if we just keep the text version of the label instead of a type that machines can operate well with. The issue with retaining text labels is that they are not readily processed by machine learning algorithms, which operate more efficiently with numerical types. There are several methods to address this issue. One common solution is one-hot encoding, which converts different categorical text values into a binary matrix representing categories distinctly. For cases with only 2 classes, such as benign and malignant, we might assign malignant as 1 and benign as 0, converting the text into numerical values. But What happens when we have multiple labels? Consider a diagnostic test for detecting Alzheimer's, where the potential labels might be Alzheimer's disease, cognitively normal, or mild cognitive impairment. In such cases, our earlier method of using binary indicators, 0 or 1, for labels is insufficient. With more than 2 labels, we use a matrix to represent labels where the position of 1 within the matrix indicates the specific condition, leading to label representations like 100, 010, and 001 for each of the 3 labels. So, the encoding in which we use 1 and 0 to represent the values is called one-hot encoding. This is just one of the several encoding methods available for handling categorical data. Now, you might wonder, can we also use the matrix approach to the binary class as well? You're correct. We can represent 01 as malignant and 10 as benign. This is somewhat similar to how we handle multiple channels in an image, where each channel in the matrix can represent a different category, similar to each color channel representing different color intensity in image processing. And to give another example of a multi-class label, an X-ray video processing task may detect for 4 total diseases, each having its own label. The labels may be tuberculosis, pneumonia, pneumothorax, and COVID for the last label. A patient may have more than one of these diseases from X-ray videos. Since there are 4 total diseases, there are 16 possible labels. If they have both pneumonia and COVID, their label will be 1001, and if they have tuberculosis and pneumonia, the label will be 1100, and if they only have pneumothorax, the label would be 0010. And if they have all the diseases, the label would be 1111. And if they do not have any diseases, the label would be 0000. If we try to look for all configurations, we would end up with 16 total labels. So, when we use this encoding technique, we as the users need to keep track of which value each attribute of the label corresponds to which. When we analyze our results, the computer will return values of 0 and 1, and it is up to us to translate those binary numbers back to the original context. To summarize, one-hot encoding transforms labels into a mathematical format consisting of zeros and ones. In segmentation, we use something called a mask to mark desired areas, simplifying the identification of specific parts of an image for analysis or processing. This technique is important in applications like medical imaging or object recognition, where precise localization of objects within an image is necessary. For instance, if we want to segment only the middle black box in a black and white image, the label would assign a value of 0 to all other pixels, with only 1 corresponding to the middle box. To distinguish between an image and a mask, consider that pixel values in an image are continuous, spanning the entire range without breaks. For example, in a CT scan, values might range from negative 2048 to a positive maximum. Segmentation, like one-hot encoding, marks only the desired areas. In this process, each unique value in the mask corresponds to different anatomical structures or features. If we want to segment multiple regions, we would denote the first area with the 1, the second area with the 2, and so on. This method is useful in multi-class segmentation tasks where each class represents a different type of object or region within the same image, improving the clarity and utility of the segmentation. Segmentation also leverages the concept of channels, similar to how we analyze images. For a 3x3 image, if we want to segment the middle and the edges, the labels might be arranged as 10 for the middle and 01 for the edges, with all other areas marked as 00. This multi-channel approach helps in segmenting multiple objects or regions within a single image, allowing for more detailed analysis and application-specific processing. I'll show this example again with the larger image. For clarity, the first mask would cover one region and the second mask another. The areas we don't want to focus on would be marked as 0, 0. The center region would be labeled as 1, 0. And the peripheral regions that we are interested in would be 0, 1 across multiple entries to clearly differentiate this mask from the other. This process shows the flexibility of segmentation in handling complex imaging tasks by allowing specific regions to be isolated and analyzed independently. Moving on to detection, it provides us with the location in terms of coordinates. Detection labels include a bounding box or B box, which specifies the location and the classes involved. The dimensions of the B box depend on the dimensions of the image or a video. Revisiting the CT scan example, in this image, let this area be the specific area we aim to detect. The bounding box for this area is defined by 4 coordinates. These coordinates establish the minimum and maximum values along the x and y axes, effectively creating a rectangular box that encapsulates the targeted region of the image. This method is important for accurately locating and analyzing specific regions within larger scans or images. Bounding boxes also play an important role in autonomous vehicle technology, where they're used to identify and track vehicles, pedestrians, and other things. Additionally, the label includes class information. For instance, if there are 3 available classes, we might represent them as 100, 010, and 001. The takeaway from this segment of the lesson is that while we focus on artificial intelligence, data structuring is a key aspect of the process. Proper data structuring is essential for the success of the model.